Hi everyone, welcome to Lecture 7. In this last lecture video for the Stats 345 class this term, we're going to get into regression. Regression is a really interesting topic and it builds upon some of the concepts we learned in correlation. And so in this video, we're going to talk a little bit about how we can predict or estimate an unknown Y variable from one or more X predictor variables. So this video, we're going to break down into a couple of different segments. The first is going to be about what regression actually is. Then we'll get into some of the unique basic assumptions of regression, followed by our process for how we create the regression line and understand some of the different regression lines that we have to our disposal. Once we go ahead and do that, we'll talk a little bit about how to compute the regression, how to calculate the F ratio, write up our statistical findings as usual, come to our conclusion statements, and last, go through some non-parametric equivalents if the assumptions are violated. So if you're ready to get started, let's go ahead and dig in. Okay, so in this first video, let's talk a little bit about regression. So regression is a way of predicting an unknown outcome variable of interest. And when I say the word outcome, we want to think about the word Y, right? What is that Y letter that we think about? The unknown value, right? The dependent variable that we talked about in comparison testing, but now we call it the criterion variable. And so Y, the criterion variable, the dependent variable, they're all representing the same thing. And our goal here is to try and estimate what that Y is from one or more X predictors. And so what we use is something that's known as a hypothetical model, because we're not actually measuring the true relationship between X and Y. Instead, we're looking at a model where we see these correlations between X and Y, and we wonder, well, if I know X for one person, can I reasonably guess what Y would be for the same person? And so because of this, the models are generally going to be what's known as linear in nature. And that really is based off of the foundation of what we learned in correlation based off the basic assumption of linearity. And so we're in the business of trying to figure out what the linear relationship is and when linear relationships exist, seeing if we can leverage and use that linear relationship to try and predict an unknown outcome variable of interest. So now let's talk a little bit about basic assumptions. So we said all term. Basic assumptions are conditions that need to be met in order for the data to show what it intends to show. And for linear regression, regardless of whether we use what's called a bivariate regression, where we have one predictor and one outcome variable, criterion variable, just like correlation, or if we have two or more predictors and one criterion outcome variable of interest. And so the conditions that need to be met for our assumptions are as follows. The first thing is that all variables, meaning the predictor and the criterion, has to be at least an ordinal level of measurement. Yes, that's right. I said ordinal level of measurement. Although we would prefer interval or ratio level of measurement, regression really works with ordinal level data because you have it organized from smallest to largest or from a smaller number to a larger number. And so because the units are moving in increments of 1 unit per piece, then we can use an ordinal level of measurement. Although we will have to do some coding procedures because we're technically still using a categorical variable and we're treating it as continuous. Nevertheless, ordinal level of measurement is the minimum criteria. All categorical variables that we choose to use, such as a nominal level of measurement, it's not really supposed to be used, but researchers do it all the time. And so we can take a categorical variable and make it continuous by making it ordinal. So for example, if I wanted to code, let's say, race as a particular categorical variable of interest, I can code 0, 1, 2, 3, 4, 5, 6, 7 for different races. And as I change 1 unit from one race to the next race, I can linearly predict how an outcome variable of interest, let's call it systolic blood pressure, how that changes based off of a 1 unit change in race. So the bottom line is that we can use these categorical variables, both nominal and ordinal level of data, in a regression analysis, which is designed for continuous data only. But when we do so, we have to code it using an organized system, such as a coding scheme using dummy coding or orthogonal coding. The third thing that we need to think about is that if we do have ordinal level data and the y variable, the criterion variable, is categorical, well, then we need to use a completely different set of procedures that's beyond the scope of this class, really, and is beyond the scope of this lecture. And that is called logistic regression, where you have a continuous x predictor as the input and a categorical y criterion variable as the outcome variable of interest. And so for those reasons, the way that regression is really designed is such that both the predictor x and the y criterion are both continuous levels of measurement. That's the ideal scenario. Okay. The other thing to think about is that when we're going to use regression, we really rely on a linear relationship. So if the x and the y variables are not correlated, then it's not going to predict. But if it is correlated, then it's likely that we can move forward and use that correlation in a regression procedure. So just some things to keep in mind. A couple other assumptions that we've checked for all term has been this homogeneity of the variance assumption, right? And so in regression, we don't use Levene's test of equality of group variances. We're not using, for example, a Mauchly's test of sphericity as we did with the ANOVAs, but instead we look at something that's known as homoscedasticity. And it's similar to the homogeneity of the variance assumption, but the difference is we're pretty much determining this schematically, looking at it graphically. And so on the left side of the slide here, you can see that we have a scatter plot. In this case, it's based off of high school grade point averages. And then you have X is the high school grade point average and Y is the first year grade point average in college. And so you can look at where the cluster of data points is occurring and generally get a sense for if the variance in X is moving in a similar fashion to the variance in Y. And when the data points are more consistently spread out as they are in the upper left quadrant of this slide, you can see that that is a relatively uniform distribution of variance. And so this is what's considered to be a homoscedastic plot. This is different from a heteroscedastic plot, which you can see in the bottom left quadrant, where you have that cluster of what's known as limited variability. So while 80% of the data points are surrounded by the brown circle, you have that 20% circulated in that little sort of oval blue circle. And so that is representing a heteroscedastic distribution because there are certain components of the variability in X that are not moving in a similar fashion to how they're moving in Y. And so I hope that's helpful. Homoscedasticity is all about verifying the basic assumption of homogeneity of the variance, but in a linear model such as this, we can use scatter plots to really help us determine whether or not that assumption is violated or confirmed. We do not have a statistical test per se, like we did with Levene's test of equality of group variances or Mauchly's test of sphericity to rule that in like we did with comparison testing. The last basic assumption then that we really need to think about before we start talking about how to create a regression line is an assumption that's known as multicollinearity. And so the assumption of multicollinearity basically means that if I'm doing a multiple regression where I have more than one predictor, is it possible that my X1 predictor and my X2 predictor, meaning predictor 1 and predictor 2, are actually correlated among themselves? And as being correlated between themselves, they don't predict the Y criterion that the whole point of the regression is trying to do to begin with as effectively as it really should be. And so when we have multiple regression where there's more than one predictor at play, we have to worry about, is the relationship between X1 and X2 strong? And because it's strong, it influences the degree to which X1 can predict Y and X2 can predict Y. This is not generally a problem in bivariate regression where you only have one predictor and one criterion. So I hope this video was helpful. In the next video, we're going to talk a little bit about how we create regression lines. We'll see you there. Okay, let's talk a little bit about how we're going to create regression lines.